Hello everyone, let's wait for a couple of more minutes, then we will start today's session. Can someone please confirm if my slides are visible and I'm audible?
Yes, sir, REB.
Okay. Okay, I think we can start today's session. Good evening, everyone. My name is Arpit Bal. I am a PhD scholar at Department of Electrical Engineering, IIT Bombay, and I'm your PMRF NPTEL TA for Digital IC Design course. And this is the 10th live session. Okay, so far, we have covered a lot of topics related to the core concepts of digital IC design. In week 1, we covered topics related to the VTH variation, the body effect, and related to drain current equation. We use the unified current equations. Then in week 2, we did some problems on DIBL, junction capacitance calculation, and PMOS transistor calculation. Week 3 was related to numericals, which were based on VIH and VIL, and also the inverter trip point. Week 4 was related to noise margin and Elmo delay. In week 5, we did questions related to power and power delay and process variation. Week 6 was mostly related to designing the CMOS schematic and electrical effort. and also capacitance calculation. Week 7 we did path delay calculation, then optimizing the delay, and logical, parasitic and electrical effort. Week 8 was related to the mirroring property of circuits, special circuits and pseudo NMOS logics. In the last week we did some questions related to adders, which are a class of arithmetic circuits. So in this week, that is week 10, so we will be doing some problems related to signed representation and multipliers. Okay, so let us start today's session. So the first question is, we have to evaluate this question. So if we have 1111 into 1100 and it is given that both are signed 2's complement numbers, okay, so what will be the result? Okay, so what is 1111 in decimal?
15.
15. No, it is given that both are signed magnitude, so in 2's complement representation.
One.
Yeah, it is -1 actually, because so in
-1.
yeah, so in the signed 2's complement representation, if we want to evaluate it, so either what we can do is, the MSB is going to have a negative sign, so we will have -2 to the power, this is 3, right, plus 2 square plus 2 plus 1, that is -8 plus 4 plus 2 plus 1, that is -8 plus 7, that is going to be -1. Either you can evaluate in this way, or what you can do is, to get the original number, okay, so 1 will represent the minus sign, then what you do is you invert the bits, that is take the 1's complement, so it will become 0000, then you add 1 to it, so it will become 0001. So either way we arrive at the same answer. Okay, so similarly what will be this?
-4.
-4, okay, so this is -8 plus 4 plus 0, that is -4. Okay, same thing you could have done in this manner as well, so whichever you find to be comfortable. So what should be our answer when we do 1111 into 1100? It should be equal to -1 into -4. So what should be the value?
4.
Yeah, okay, that is, it should be 0100. Okay, so this we did by converting things to decimal. How about we do the step-by-step multiplication, like how we do the binary multiplication, right? Okay, and just remember that both are signed 2's complement numbers. Okay, let us verify that whether we arrive at this answer or not. Okay, so the first partial product will be all zeros, second partial product will be all zeros, third partial product will be 1, 1, 1 and 1. What will be the fourth partial product?
Still 1, 1, 1, 1.
Think again. Are you sure that it is going to be 1 1 1 1?
If both are signed, then both the MSPs will have negative associated with them. So negative into negative will be positive.
Yeah, it should be
So all will
positive.
be 1 1.
No, but if all are 1 1, then it will mean the MSB is going to be 1. So it will represent a negative number.
The first 3 bits are negative. Last MSB is positive.
So what is going to happen is, so we basically multiply this with this. This is already a negative number. Okay, and if we are multiplying with this, then it will become a positive number altogether. So in this case, we should not write 1 1 1 1. Okay, it should be the positive form of that 2's complement. Okay, and what will be the positive form of 2's complement? So if we have 1 1 1 1, okay, you take the 1's complement first plus 1, so it will be 0 0 0 1. Okay, zero, 0, 1, and this is 0 1. Okay, so we arrive at the same answer as plus 4. Okay, so whenever you are doing 2's complement multiplication, be careful about the MSB. Okay, otherwise you will end up with the wrong result. So let us assume that if we would have taken all ones, then it would be 1 1 1 and 1, right? So what would this answer would have been if I would have taken all ones in the fourth partial product?
One 0 1 1 0 1 0 0.
Correct. So that is not equal to 4, right? So we would have arrived at a wrong answer. So we need to be careful while multiplying the MSB, okay, at the end. Okay, I hope that thing is clear. So part A is done. What if both are unsigned numbers? Okay, I need to add a slide. Okay, so the next bit is if both are unsigned numbers. So if both are unsigned numbers, we will just do the multiplication as it is without bothering about the positive or negative. Okay, so this will be 0 0 0 0 0 0 0 0 1 1 1 1 1 1 1 1. Okay, 0 0 1. This will be 1 1 0. This will be 3. So it is 1 1. This is 3 again. 1 1. This is 0 1. Okay. So what is the value in decimal? This is 4, this is 16, this is 32, this is 64, 128. Right?
180.
Yeah.
180.
Correct. So this is 160 plus 20, that is equal to 180. Okay. Is everyone clear with question 1 or is there any doubt? So to solve question 1 part A, you can straightforward use this method, okay, because it is relatively simpler. Okay, but if you want to know how the complete multiplication thing works for both the cases to make a make an apple to apple comparison, what you can do is you can use this method and check your understanding, that whether you have understood the multiplication part correct when it comes to signed numbers or not. Okay, then there is another important thing. So if it would not have been a 2's complement representation, then what should be present here if it were a unsigned number?
Present where?
Here, like I have marked this question mark.
One.
No, if it would have been unsigned. So let's say I'm saying that I have a number 110. Okay, if it were unsigned, I could have told that I can also write it as 00110. Right? It does not change my value. Okay, so in this position I could have put a 0 and done the evaluation part. Right? But when it comes to signed number, we need to ensure that the sign is preserved. Okay, so we have to go for something called a sign extension. Okay. Okay, so I hope question 1A and 1B, both the parts are clear. Shall we proceed to the second question, or is there any doubt here? Okay. Given a signed 2's complement number p equals to 1011, if p into q equals p to the power 5, then what is the value of q in 16-bit 2's complement representation? Okay, so we are given p equals to 1011. So what will be its value? And it's a 2's complement number.
-5.
Okay, yeah. This is -8 plus 2 plus 1, that is -5. Okay, and it is given that p into q equals to p power 5. This implies q is equal to p power 4. Okay, so what is the value of q?
$625.
Yeah. Okay, so what is its 16-bit 2's complement representation? What will the sign bit be? The MSB.
0.
Yeah. And what is its decimal representation? Binary representation. 625.
Yeah.
100111001. 001.
Yeah, 001. And rest you can append the zeros. This is 4, 8, 12 and 3 more zeros. Okay, so this is the 16-bit 2's complement representation. Okay, so this was our question number 2. Okay, moving on to question number 3. What is the critical path delay for a 8x8 array multiplier? Okay, given t and equals 2 and t carry equals 3, t sum is 5, and assume that the multiplier is made using full adders. Okay, So what is my
76.
76? Yeah, I think that is correct. So what is the formula?
T and plus n plus m minus 2 times t carry
N plus m minus
minus 3
Yeah,
3 times t carry
yeah,
plus m minus 1 times t and
yeah. T sum, right?
t sum. Sorry, t
Yeah.
sum.
Okay, and in this case our n equals to m equals to 8. Okay, so we have t and given to us as 2 plus 8 plus 8 minus 3 into t carry is 3 plus 8 minus 1 into t sum, that is 5. 2 plus this is 16 minus 3, that is 13 into 3 plus 7 into 5. 2 plus 39 plus 35. Okay, that is 70. Is this correct? 4? Yeah, 76. Okay. Is my screen visible? I think there is some lag.
No, it's visible.
Okay, okay. Okay. So what is the minimum and maximum value for a 7-bit 2's complement number? Okay. Okay, let us start.
63 is the maximum.
63 is the maximum. Okay. So for maximum, what should this bit be?
0.
Okay. And the rest can be 1.
1.
Right. So that is because, so putting a 0 here will ensure that the sign is positive. Okay. And the rest, the complete magnitude can have a positive value. Okay. So if I put everything as 1, then I have 1 plus 2 plus 4 plus 8 plus 16 plus 32, right? That evaluates to, so this is 6 plus 1 7 plus 24 plus 32, that is my 31 plus 32 equals 63. Okay, so this is for maximum value. What about minimum value?
Minus 64.
Okay, so what will be my 6th bit?
1.
Yeah. Okay, and okay, someone is, yeah, and what will be the rest of the bits?
0.
Are you sure? Are you sure that it is 0?
No. Then it wouldn't be minus 64.
No, I'm just playing with you, but are you sure that it is 0? Should it be 0 or all ones?
All ones will give us minus 1, so that's not the minimum value.
Yeah. So what should be the minimum value then?
1 and all zeros.
Yeah. Okay. So 1 and all zeros is going to give me, so this position will be, this is the 7th bit, right? So minus 2 power 7, sorry, 2 power 6, that is minus 64. Okay, so this is actually a point of confusion. So what I have seen that few people while solving for this kind of problems, that minimum value and maximum value for given set of bits. So what they do is they think because the maximum value in the positive direction was 0 and all ones, they also do the similar mistake in the minimum value case. What they do is they take 1 in the MSB to make it negative, and they put all ones after the MSB. Okay, but as Prajwal mentioned, that if you put all ones after the MSB, then this entire set is going to be a positive number. This is the only negative number. Okay, so we need to ensure that the positive part is as minimum as possible to obtain the minimum value. Okay, so it will, the minimum possible value for the positive number is 0. So this has to be all 0. Okay, so please keep that part in mind. Okay, so the maximum value is 63 and minimum value that can be obtained is minus 64 for a 7-bit 2's complement representation of a number. Okay, moving on to the next question. What is the critical path delay for a 8x8 carry save multiplier with a ripple adder as the vector merge stage, and T and equals to T carry 3, T sum as 5? Assume that the multiplier is made using full adder blocks only. So we have T carry save equals, so what will it be? T and plus does anyone remember?
I haven't completed it yet.
Oh, okay. So anyone who would like to give it an attempt? Okay, so this will be m minus 1 T sum plus n minus 1 T carry plus T sum. So this is from the vector merge stage, and it is mentioned that we are using a ripple carry adder. Okay, so what will it evaluate to? Your m is 8 and n is 8. Please try to evaluate this.
$63.
Yeah. Okay. Okay. So okay. So moving on to the next question. So consider the ALU that is shown to you on the right hand side. If the operands are in 2's complement representation, which of the following operation can be performed by suitably setting the control lines K and C naught only? Okay, and plus and minus denote addition and subtraction respectively. Okay, so take a moment and read this question and try to answer this question. Okay, meanwhile I'll add a slide here. Okay, so the options are given here. Anyone would like to give it a try? Okay, first tell me, is a plus b possible here?
Yes.
Okay, so if a plus b is possible, then I have two control knobs with me, k and c0. What should be my k and what should be my c0?
Both K and C0 must be 0.
Okay. Does everyone agree with this, or is there any other answer?
Sir, can you repeat once again?
Okay, so this ALU is given to you and the operands are in 2's complement representation. Okay, K and C0 are the control knobs that are available with you. Okay, and using those control knobs you can perform various type of functions between A and B. Okay, so which functions can be performed using this module? So that thing you need to mention. Okay. And after that, the first thing I asked is a plus b possible? So one student mentioned that if k equals to 0 and c equals to 0, then we can get a plus b. So what I want to know is everyone agreeing with this solution, or is there any anyone to challenge this solution that a plus b will be performed if both k equals to 0 and c equals to 0? Okay, let us see whether k equals to 0, c equals to 0 will give me a plus b or not. Okay, so to get a plus b, okay, so it means my b1 should appear here and b0 should appear here. Okay, and whenever you are performing a XOR operation, what should be one of the operands such that the other operand is obtained as it is?
0.
Correct. Okay, so it means whenever you have a XOR gate, if one input is x, then other one should be 0. So if you have 0 as one of the inputs, then the output is going to be x. Okay, that is the true form of the other input is reflected. So it means k equals to 0 is correct to get b here. Okay, now the question is, what should be the value of c?
0.
Yeah. Okay, so if c equals to 0, then the complete a0 b0 is added to a1 b1. Okay, so a plus b is possible. Similarly, can someone tell me, is a minus b possible?
Yes.
How?
If k equal to 1,
Okay.
if k equal to 1, we'll get inverted inputs. B0 is B0 bar, B1 is B1 bar.
Okay.
So basically, the whole value of B is its one complement value. So when you add it with A, you get A minus B.
Okay, but the representation is in 2's complement.
Oh, right, yeah.
Okay, you are going in the right direction, but just think a bit more. So you have done the inversion correctly by mentioning k equals to 1, because wherever you have a XOR gate, okay, and you have applied 1, then the output that you will get is the complement of the second input. Okay, that part you are absolutely correct. You have another tuning knob available with you, C.
Yeah, C naught also we have to keep one. Then it will be basically the number is in 2's complement form.
Correct.
So if all the XOR gates give us inverted inputs, then
Correct.
we have 1's complement of that number.
Yes.
We have to add 1 to get the
2's
number in
complement.
negative value.
Correct.
And when we pass it to full adder, we'll get A minus B.
Correct. Okay. So if I put K equals to 1 and C equals to 1, okay, then I will be able to get A minus B. And the reason being, with putting K equals to 1, I get the inverted forms of B. That is the 1's complement. From 1's complement, if I have to get the 2's complement, I need to add a 1. Okay, and that 1, I will get it by setting C naught equals to 1. Okay, so A minus B is also possible using this module. Okay, is A plus 1 possible?
Yes.
How?
If the value of B is adjusted, then we might get A plus 1.
Correct. So A plus 1 is possible conditioned to the value of B. Okay, because we already proved that A plus B is possible using this ALU. Okay, so A plus 1 will also be possible provided B is going to have the value of 1. Okay, but A plus 1 is not possible always for all values of B, and because of which option A is correct. Okay, because that condition is satisfied only for one value of B. Okay, and it is given to us that the only controls that is available to us is K and C naught. We do not have any control over B. Okay, so if B is having any other value, then the A plus 1 condition won't be available to us. Okay, so let me summarize this particular question. XOR of a number with 1, we will get the number's complement form. Okay, and XOR of a number with 0, we get the number's true form. Okay, if K equals 1, we get okay, because K equals to 1 will set B to its 1's complement form, and C equal to 1 will add 1 to the B's 1's complement form. That will imply we will have minus B. Okay, similarly, if K equals to 0, then B's true value is processed further, and keeping C equal to 0, we get a plus b. Okay. Similarly, a plus 1 if and only if b equals to 1, not for any other value of b. Okay. So this particular question appeared in GATE Computer Science 2003. Okay. So they have a portion in digital logic design. So this was from there. Okay. So is everyone clear with this question? Is there any doubt? Is there any doubt in this question? Okay. So on the right hand side you can see a collection of some components like full adders and XOR gate, right? So XOR has this interesting property that if any one of the input of XOR is 0, then the output is going to be equal to the second input. Okay. But if any one of the input is 1, then the output is going to be complement of the second input. Is this part clear? Okay. So now we are given some inputs A1, B1, A0, B0, C0 and C1 and K. And it is told to us that we have control over only two things, that is K and C0. Okay. And it is asked that using these inputs A1, B1, A0, B0, can I perform A plus B, A minus B and A plus 1 or not? By using only these two knobs, that is K and C0. Means you can take any value for K and C0 and you need to perform these operations. Okay. So that is what we have to determine whether these operations are feasible or not. Okay. Then what we observe is, to get A plus B, if we set the value of K equals to 0, okay, then the true value of B will appear at the input of the full adder here. Okay, so that's why we set K equals to 0 first. Next, we just need to put C0 equals to 0 so that our A plus B operation is performed properly. So that is how we see that A plus B can be performed by setting K equals to 0, C equals to 0. That was the first thing. Now the next thing, can we perform A minus B? Okay. So to perform A minus B, so I can write this as A plus 2's complement of B. Right? It means if I have a adder, I can just give two inputs, A and B's 2 complement. Correct? Is my screen stuck?
No.
Okay.
No, it's fine.
Okay. Actually, it is not getting reflected on. Okay. Yeah. Okay. So I need to give two inputs. One is A and another one is B's 2 complement into the full adder. Okay. So let us break down how to generate these two complement. Okay, that will be 1's complement of b plus 1. Okay, now we observe that to generate 1's complement we have this facility available. XOR gives us this facility. Okay, now we need an additional 1 from somewhere. So who can provide me that additional 1? So we will use C0 to get that additional 1. So what I will do is, I have full adder, I'll take A, I'll take B's 1 complement and another 1 to get this thing. Okay, that is nothing but 2's complement of B, and A plus 2's complement of B is nothing but A minus B. Okay, does that answer your question? Okay, and A plus 1 can also be implemented because we have already proved that A plus B can be implemented, but A plus 1 can be implemented only if B is having the value of 1. Okay, so it won't be true for all cases of B, and because of this reason we are selecting option 1. Okay, so in this particular slide I have summarized what all we did, so please go through it if you want. Okay, so moving on to next question. We consider the addition of two 2's complement numbers bn minus 1, bn minus 2 up to b0 and an minus 1, an minus 2 up to a0. A binary adder for adding unsigned binary numbers is used to add the two numbers. The sum is denoted by cn minus 1, cn minus 2 dot 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 up to c0, and the carry out by cout. Which one of the following options correctly identifies the overflow condition? Now let me tell you what do I mean by the overflow condition. Okay, and then based on that you determine which one of the options is correct. So when I say that an overflow has occurred, it means like two same signed binary numbers are added and the result of these numbers has different sign. Okay, it means from the carry out of one of the stages, one carry has been generated and it has somehow entered the MSB and it has altered the sign. Okay, is everyone clear with the overflow condition?
Sir, can you repeat once again?
Okay, so when I say that there is an overflow, what I mean to say is I have taken two numbers. Okay, let us say I have taken two numbers A and B. Both A and B are having positive sign. But when I have done the addition and I am representing A and B in 4 bits, and after doing the A plus B, what happens is the result that I obtain has a negative sign. It means the MSB is 1. Okay, that is definitely wrong. Okay, but I have obtained this result, so it means there is an overflow condition that has occurred.
Okay, sir.
Okay, so with that explanation, can someone tell me which of these options are correct or the most suitable one? Okay, and whatever the output is, it is represented as Cn minus 1, Cn minus 2, Cn. Okay, so An minus 1 and Bn minus 1. It is the MSB that contains the information for the sign. Okay, so let me make a truth table. Not a truth table, but just to represent whether it's a carry out or not. Let's say both these numbers are positive. Can someone tell me what should be my Cn minus 1?
Zero.
Yeah, ideally it should be 0. But if there is an overflow,
1.
1.
okay. Similarly, if my An minus 1 is 1, Bn minus 1 is 1. In case of
0.
overflow, yeah. Okay, so looking at this, can someone tell me which one of the options are correct?
Why is overflow condition 0?
Because see, the sign is getting changed. An minus 1 means this is a negative number. Bn minus 1 means this is a negative number. Correct. Can I ever get a positive number by adding two negative numbers?
Okay, yeah, no.
Yeah. Okay. So from this representation itself, like, we have the answer. So can someone tell me which one is the correct option?
But in first case as well, you took both as 0. That means both are positive.
Correct.
And if you add two positive numbers, there is no way you will get a negative number.
Correct.
Then why is overflow condition 1?
What if An minus 2, it generates a carry somehow? Okay, and that carry gets propagated here. Understood, right?
Yeah, I got it.
Okay. So what is the appropriate option to identify the overflow condition?
A.
No. So An minus 1, Bn minus 1. If An minus 1, Bn minus 1 are both 0, means if both are having a bar, then Cn minus 1 will be in true form. Okay. From the second condition, if An minus 1, Bn minus 1 are both in true form, Cn minus 1 will be in complement form. Okay, so option B is correct. Okay. Okay, so even this one was previous year, I think 2015 GATE question. This was for electronics, I guess. So yeah, this appeared in, I think, 2015 or 2005, I don't remember, but yeah, this was also one of the questions from GATE. Okay, moving on to the next question. So you have a number given here, 111100. Okay, and you have to identify which ones are the true statement. So what is the sign 2's complement representation of this number?
00001.
Wait. One can't be. Yeah, one can be at the end. Okay, let's see. So to get the sign 2's complement representation, I need to get the 1's complement first.
You have to put one more one.
Yeah.
MSB.
Correct. MSB. Oh, okay, sorry. This
There
is
are 4 ones in the question.
Yeah. Okay. So this is my ones complement. To get the twos complement, I'll do +1. So it will be 0. Okay. Is this correct?
Yeah.
Are you sure?
But negative of that number, that's it.
Yeah,
The value is correct, just negative of that.
correct. So it has to be sign extended in a way that 1 is being extended to the left. Right? So it will be something like 1 1 1 1 1 at the end, 2 zeros. So out of these following options, which one is correct?
Last but one option is correct.
Okay.
Option A and option C are correct.
Option A and
First and third.
Yeah, correct. Okay, because first is just the sign extended version of the third option. Okay, so option A, C and option D. These three are the correct options for this question. Okay, so these were the set of questions that I planned to cover today. And there is one more thing on April 17th, I guess. Okay, so we will have an extra session, and in that extra session what I am planning to do is I'll cover a tutorial of a tool. So that is an open source tool, and so I think that will be helpful for anyone who is interested in digital IC design. Even it can be used for analog IC design as well, yeah, so I'll cover a brief tutorial of 2 hours on April 17th. So the exact date and time, it will be announced on the NPTEL forum, NPTEL announcement page. Okay, and it will be mentioned as a revision session. So instead of spending more time on the revision part, I thought I'll cover that tool, and it will be helpful for you guys. So if anyone wants to practice transistor level designs and stuff. Okay, so
I'm sorry, what exactly are you planning to do on April 17th?
Yeah, so I'll do a tutorial session on a open source tool.
Okay, got it.
Yeah. Okay, so question 8, please. Okay, yeah, so we have this thing available with us, this number. Okay, and oh wait, ignore this part. Yeah. So this is for getting the unsigned form. Okay, so for getting the unsigned form, I did that one. Wait, I just got confused. Oh, okay. Wait, we don't need to do this much. Okay, so basically we have this number with us, and the direct signed tools complement representation is available with us here. Okay, so if it is an unsigned number, then to do the, like, you can just pad zeros. It's like if you have 1 1 in unsigned form, it is equivalent to 0, 1, 1, 0, 0, 1, 1. Okay, but if 1, 1 is given as a signed number, then that will be equivalent to 1, 1, 1 or 1, 1, 1, 1. Okay, as many ones as possible. Okay, so basically in the first part what they have done is they have added a few more ones. Okay, and if you just extend the sign bit, that is the MSB, then the value of this number does not change. Okay, and the same thing has happened with the third case as well. In third case also they have added 2 extra ones, and that is also sign extension because it is mentioned that it's a sign 2's complement number. Okay, but if I treat this number as an unsigned number, then I need to append 0 before it. Okay, so that is what has happened in case number D. You don't need to do this whatever square thing we did, because I thought that they wanted to convert to 2's complement. So, is that clear? Shilpa. Okay. Yeah, so let us revisit what we covered today. Okay, so today we started with sign 2's complement multiplication, and we saw that we can either convert those numbers into decimal and perform the multiplication and go back to the 2's complement representation again, or we can go by the brute force method of computing the product of the two numbers in sign 2's complement representation. The second condition was given to us that if both the numbers are unsigned, okay, then you just simply need to perform the multiplication as you do by generating the partial products without bothering about the sign extension part. Okay. Next question we did was related to figuring out what means the value of Q is. So we were given P into Q equals P power 5. From there we figured out Q equals P power 4. Okay, and P value is given to us. Okay, that thing we converted to equivalent decimal representation, and that thing we again converted into the 16-bit representation in 2's complement form. Next question was related to array multiplier, and we were supposed to figure out the critical path delay for this configuration. Okay, and we have the formula available with us, that T array multiplier equals T and plus N plus M minus 3 into T carry plus M minus 1 T sum. Okay, and in our case it was a 8 cross 8, so N equals to M equals to 8, and you can evaluate the answers. Question 4, we figured out what is the minimum and maximum value for a 7 bits 2's complement number. So maximum value will be obtained when the number is positive. To make it positive, make the MSB 0. Okay, after making the MSB 0, put all ones in the remaining bits. Okay, and then we obtain 63 as the maximum possible value. Similarly, to get the minimum value, we need to first set it to negative. To set it to negative, put a 1 in the MSB, that is the 6th bit. Okay, and all other values, it should be 0 to obtain the minimum value. So we have minus 2 power 6, that is minus 64 as the minimum. Next question was related to carry save multiplier, and we had to figure out what is the critical path delay for the carry save multiplier. We use the formula that is available with us, and the answer is 63. In next question, so we were given an ALU, and we were supposed to mention what all operations can be performed using this ALU block if we have control over only two knobs, that is K and C knob. And we observed that we can do A plus B, A minus B operation for all values of A and B using this ALU block, and A plus 1 can be performed only if the B input is going to be 00001. Okay. In question 7, we try to figure out the condition so that the overflow is identified correctly, and the overflow is defined as the if two same sign binary numbers are added and the result of the numbers have a different sign. Okay, and we have to identify that condition. So to identify that condition, we wrote the possible inputs and the subsequent condition that is going to identify whether an overflow has occurred or not, and based on this, option B is correct. In question 8, we were supposed to figure out what were the correct statements. So we are given a number and we just need to do either sign extension or normal extension of the number. If it is a unsigned number, if 11 is given as an unsigned number, then 011 is same as 11, and 0011 is same as 011 or 11. Okay, had it been a signed number, we need to see whatever is the sign present at the MSB and we need to extend it, and the value of that number will remain same even if there is a sign extension. So based on that, option A, option C and option D are correct. So these were the set of questions that I planned to cover today. The recording of this session will be available by 8:30 on the YouTube channel, and these slides will also be available by the NPTEL team. So in that Excel sheet, I'll upload it on the Google Drive. So yeah, that's all we have for today. If anyone has any doubt, then they can let me know, else we can wrap up today's session.
There's a session meeting tomorrow with the instructor. What is it about?
So usually means if you have any one-to-one question that you want to ask to the instructor, so I guess once in yeah, this is happening for the first time, right? Or did it happen beforehand?
I don't know. This is my first NPTEL course.
Okay. So usually there is a one-to-one interaction for some courses where the instructor interacts with the enrolled students. So if you have any query, if you want to discuss anything with the instructor, then I think a form will be floated with you. So you can ask your respective question, maybe related to the course. If you have any doubt which is not covered in the subject and you are interested to know more about it, even that thing I think you can put. And yeah, like it's like a interaction, so it will be a two-way thing, right? So if you have any feedbacks to give, so you can use that one, and the instructor will also gauge like how is the students' reception for this particular course. So yeah.
Okay, thank you.
Yeah, sure. Okay, if anyone has any doubt, please let me know, else we can wrap up today's session. Thanks everyone for joining. Okay, I'll still be around here. If anyone has any doubt, then please let me know. Hello. Yeah. Hi, Rishendra. So, we have completed today's session just now. So, do you want me to go through all the questions that we solved today? Hello. Uh, you are not audible. Okay. Okay. Sure. Yeah. Hello. Yeah. Are you saying something?
Nothing, sir.
Okay. Okay. Yeah.
Hello.
Hello.
Sir, can you explain the lecture that sir told in last lecture?
Last lecture, what was it about?
Means sir has appended ones to the means when we are doing multiplication
Yeah.
using 2's complement.
Yeah.
Uh, when we are multiplying MSBs, both MSBs.
Okay.
Uh, means when we are multiplying the multiplicand with the MSB of the multiplier,
Huh.
sir has appended ones to the right, sir.
To
Means
the right. Okay. Just a minute. Let me open that.
okay.
So, are you referring to this, like, let's say x3, x2, x1, x0, y3, y2, y1, y0? Okay, and you have a set of outputs. So he added once here. Is this what you are referring to?
Yes, sir. Yes, sir. Why should we add that once? I have a doubt.
Okay. So one thing that so this represents the sign bit, right? Y3.
Yes, sir. Yes, sir.
So if y3 is multiplied with anything, okay, so it means that
It should be a negative number.
negative number, correct? And
Yes, sir.
so because of this, so whenever we are going to do the evaluation, like the complete addition process, so the entire partial product should be negated, right?
Yes, sir. Yes,
let's
sir.
say let's say one okay, let me give you one example. Let's say 101 into, okay, this will be a big example. Let's say 10 into 11. Okay,
Yes, sir.
if assume that it is unsigned. So when you are doing this, what you are doing is, so you have this position vacant.
Yes, sir.
So actually it is not vacant, there is a 0 present here.
Okay, sir.
Understood? And if this partial
okay.
product has a 0 present and you want to take the inversion of that, then it will be 0, 1, 1.
Yes, sir.
Correct. So it appears like a
Yes,
1
sir.
appears out of nowhere, but it is actually inverting that partial product.
Yes, sir.
Understood now?
Yes, sir.
Okay. So that's how those ones appeared there. So this was supposed to be vacant, but because it is multiplied with y3, so we have to do the inversion, and that vacant spaces were occupied by 0 earlier. Now when inverted, it becomes 1, 1.
Sir, but when we are using 2's complement, we should add 1, sir.
Yeah, that
then
one
it
is
should
also
be
added.
again 0.
Yeah, that one is also added. So because to get the 2's complement, one thing that we need to do is get the 1's complement. That is complement all the bits, then plus 1. So if you recall, so sir added 1's at the right hand side, then he added a plus 1 in between.
Yes, sir, but we should add at the LSB.
Um, yeah, this is LSB now.
Yes, sir. Yes, sir.
Okay.
Okay, sir. Okay, sir.
Okay.
Understood, sir.
Yeah.
Okay, sir. Thank you, sir.
Yeah, sure.